All right, should be recording. First of all, did everyone hear the announcement about the last date of the school year? That instead of being a half day on the 19th, the last day of school will be a whole day on the 18th. So they just cut off that last half day. So that is a school announcement for you guys. All right. Remember what we've been talking about? We've been talking about solar system formation, but so far we've only been talking about our own individual solar system for the most part. What we're going to talk about today is our ability to see solar systems that exist beyond our own so that we can compare how ours is to all the other ones we could see in the galaxy. Why do you think this might be an important bit of information to add to our theory, to add to our understanding of our own solar system? Any ideas?
To see if there's other solar systems, planets like us.
Yeah, see if there's any like us, see if, how much like us they are. Good, because, let's say I'm studying a type of animal I've discovered in the forest. Do I just pick one individual and follow him around for a while and then say that I understand how the whole species is? No. How come, Brad?
Because not all the species would do the same thing in the same area.
Right, and so not all solar systems might be just like ours, and there might be different things about them. So when we look at other solar systems, we can use that information to build a whole picture of how all solar systems are alike and dislike. Right. This graphic that I put up here is actually over a year old. So when it says over 1,000 confirmed planets, it should say over 1,800 confirmed planets. And we'll look at some more recent things in a while. But it's a really good graph because it's going to show you some categories of what we're going to be talking about. First word to introduce is exoplanet, vocab word, exoplanet. Do you have any idea what that term specifically might be referring to?
Outside the solar system?
Yeah, a planet that's outside of our own solar system, because the prefix exo, have you heard that in any other term, vocabulary? Like an exo suit, something you put on over the outside, or what do crustaceans and arthropods? Exoskeleton, right? Exo on the outside. So these are exoplanets, planets that are outside of our own solar system. Sometimes they're referred to as extra solar planets. And this means the same thing, just outside of our own solar system. Based on the size of the planets, this was and still is a pretty accurate representation of the kinds of planets we've been able to observe and discover in the solar systems that are surrounding our own. So what do you notice about the numbers and the sizes of planets? Is there any pattern?
The larger the number, the larger the planet.
Yes, the larger the planets, the more we've discovered. So as of a year ago, they found over 700 big, huge Jupiter planets, but only a handful of planets the size of Earth or smaller. So we're going to talk about why. Be thinking of ideas of why you think that might be. Do you have any ideas right now? Why might we have a whole bunch of these discovered that are really big, and not very many of these that are smaller?
They're harder to find.
Why might they be harder to find?
They're smaller.
Because they're smaller, yeah. It's really that simple for most of the ways we're going to talk about. So, how on earth do I observe a planet that's orbiting another star in the first place?
Big telescope.
A big telescope is usually required, yes. The truth is, it's not easy, and we're going to look at a number of things that are kind of tricks that astronomers and physicists can use in order to find out if there's a planet orbiting another star, and if there is, what kind of information can we learn about it, given what we see through a telescope. Here's the first key piece of factual evidence that we need to understand to see how I could find out if there's an exoplanet around a star. We've talked about gravity. What do you know about gravity? Anyone want to give a basic definition of gravity?
It's what keeps us in place on Earth.
It's what keeps us in place on Earth. True. It's a force. So what makes the force? Like what does something have to have in order for it to make gravity? Mass. Right. So Earth has mass. The sun has mass. True or false? Earth is orbiting the sun.
True.
You said it because you have an idea, or because it was kind of a transparent question?
That's what.
Yeah, okay, so you're right. Okay, good. The Earth has mass, the sun has mass, so do you think the sun is feeling any gravity from Earth? Because the Earth has mass, the Earth is what's generating the gravity that's pulling you down. So could that same gravity be affecting the sun?
No, because the sun has more mass.
The sun does have much more mass. So when you said no, that's a common misconception. The truth is that it is affecting the star, but it's affecting the star a lot less than the star is affecting the planet. Because you're right, that we said how much of the solar system's mass is bunched up inside the sun, out of all the stars, the sun, the planets, and the moons, and the asteroids, how much of all the total stuff is inside the sun? What percentage?
90%.
Bigger. So 99% is bunched up in the sun, and all the planets and all the moons make up 1% put together. So little tiny Earth is, a fraction of a percent of all the mass. But it still is massive. It has enough gravity to keep the moon in orbit. It has enough gravity to keep you all on the ground. So the Earth has a tiny effect on the sun, even when the sun has a big effect on the Earth. So in truth, they're both affecting each other, is the point I'm making. It's not just the sun is doing 100% of the work. The sun has most of the mass, so it has most of the gravitational force, but it's not all of it. So just like we are orbiting around the sun, from a certain point of view, if you look at the diagram I've been having on the board, the sun is also orbiting around us, or more accurately, the center of mass between us. That's a term I should talk about. Center of mass. We'll go over to this board. If I have one block of material that's 10 kilograms, and I put it there, and I put another block of material that's 10 kilograms, and I put it there, where is the center of mass? In the center, exactly. It's right in between them. If I take the mass of all of this, I find the central point between them. So if I take a star and a planet, the center of mass isn't going to be dead center in the star because there's this mass over here. It's going to be a little bit this way from the very center. And planet is not orbiting the star, the planet's orbiting the center of mass between the planet and the star. And the same thing for the star. The sun isn't just sitting there perfectly stationary. It's moving around a little bit in its own circle as it orbits the center of mass between the two things, between the planet and the star. So the key point in all of this is that I could see the star moving. He's moving around in an itty bitty circle because there's a planet orbiting him. If there's no planet orbiting the star, then he would just be standing completely still and not moving. So when I look through a telescope, which do you think is easier to see, a planet or a star? Star, right. So when I look at the star, there are a couple of different ways that I can tell if the star is moving, like in a little tiny circle. We call it wobbling. We can measure the star wobbling, then if we can do that, there must be something causing it to wobble. There must be a planet that has a little bit of gravity that's making the star move in a little circle. So, first method, and these are things to keep in your notes, is the astrometric method. Just looking at the diagram, what do you think is going on? Here's my telescope, here's my star, here's a planet that I cannot see because planets are very tiny and aren't giving off a lot of light. So what is it I'm measuring about the star in order to tell there's a planet there?
Where it is.
Where it is, right. If I have my telescope and it's a very high magnification and it's a very high precision, and I measure the star's position as being there, in that exact coordinate, then as I watch it night after night after night after night, I might see it slowly change position from here to here to here to here to here, and I can see this very, very, very small movement with my precise instruments that are going one way and the other, and one way and the other. Something has to be causing that movement, right? There has to be a planet whose gravity of the planet is tugging that star one way and then tugging the star the other way as it goes around and around and around. This motion is the side-to-side motion. We call it the transverse. Have you seen that term pop up in geography or trig class? Transverse? You will. It's just side-to-side motion. But that planet could be orbiting like this. Is there a kind of motion in my hand that's not just side-to-side? What is it? Circular, which contains not just this way, but also going towards you and away from you, going towards you and away from you. So that's what the second example on the next side is. Radial velocity. Radial velocity just means the velocity going just towards you and just away from you. No side-to-side motion. That's what the radial means. Here, 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 here. We haven't talked about it yet in class, but you might have heard of, have you heard of red shifting or blue shifting? I know I talk about it with my 8th grade class. There's a very simple way of telling whether an object in space is moving towards you or away from you. You don't have to understand the particulars right now, but if I look at the light and it's redder than it should be, then I know that it's moving away from me. And if I look at the light and it's bluer than it should be, then I know that it's moving towards me. Just accept that for now. We'll talk about it more when we talk about stars in the next unit. But I could look at the light from a star, and I could look at the very specific color of the light using my telescope instruments. And I could map the color. Here's my rainbow. I have Roy, G, Biv, going from one side to the other. and I can look at one specific color coming from that star, and I measure it very precisely. And over time, if the star is wobbling like this, and it's going away from you and towards you and away from you and towards you, then this light will get a little bit redder, and then a little bit bluer, and then a little bit redder, and a little bit bluer as it goes back and forth and back and forth and back and forth. And it's a little tiny wobble caused by the star. So those are two ways the planets can affect the star so that I can tell if there's a planet there. Any questions so far? Questions, curiosities, comments, ideas? Okay. It may not seem like it, but because of the high precision of the measurements and because of math and calculus and things like that, you can find out a lot of information about the planet besides just that it's there. Okay, I can find out the amount of time it takes the planet to go around the star. I can find out, depending on the circumstances, how massive the planet is. I can find out the size of the planet. So there's a lot of things I can tell from dissecting this information, but we're not going to worry about calculus in this class, thankfully. There's another way I just wanted to mention really quick, because it actually came up in the news just the other day. If anyone watched the headlines, there was an astronomy piece that focused on this method of seeing things. It's called gravitational lensing. Here's gravitational lensing. Let me write it up here. Gravitational micro lensing. Basically, if an object is generating enough gravity, the gravity bends the light and magnifies it. Bends and magnifies. So you can use this to find planets because a planet has gravity. And so if you very closely observe the star in your telescope and you see the light behave in a certain way, it's because I can tell that the gravity of the planet is influencing the light. See, if I have, here's a distant star, this is like a background star way, way far away. Here's a star that has a planet around it. The gravity of the planet could bend the light towards you, and it would look different than if it had no planet whatsoever. The key point to remember is that gravity can bend and magnify light. The reason this was in the news wasn't to find a planet, it actually was finding a supernova way, 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 way far away. And the reason it was interesting is because, okay, here's this galaxy, has this nice pretty spiral arms, right? The big bright spot in the middle. And the supernova happens directly behind the galaxy, even further away. There's like millions of light years past. But you can see it because as the light was coming from the explosion and it was passing through the galaxy, this galaxy, made of millions of stars, has so much gravity that it bent the light around it, not just in one way, but in all four different ways. You could see the same explosion here, and here, and here, and here. You could see the same explosion in four different places because it was like four different magnifying lenses happening. And even more interesting is they're able to predict that since it takes a different amount of time to go from this way because the light has to travel further to go around, that they're going to see it again. There's a fifth one that's going to pop up in the future. And you can see the supernova happen all over again, even though it already happened. It's already been here 4 times. Weird stuff. Gravity, relativity. We'll talk about it in physics. Here's an even stranger example. You see that big swirl going on right there? That doesn't really look like that. That is one normal, average, perfectly reasonable galaxy. But this thing in front of it is just aligned to where this is in the background, this is in the foreground. So as the light from this galaxy passes through this area of space, it gets warped and bent around it. And so this galaxy, which should look completely normal, looks like a bent thing you'd see in a magnifying glass because of the gravity of the object in the foreground. All those, though, those 3 methods, the astrometrics, watching it move back and forth, the radial velocity, watching it move towards you and away from you, and then the micro lensing due to gravity, those are difficult to measure. This is the one you're going to put a star next to on your paper. This is the one that is the easiest and the one we've used the most often in order to find planets around stars, and it's called transit, the transit method. Have you encountered the term transit as just a vocabulary word? What's transit mean? To pass in front of, exactly. If it's something is transiting, it's going to move past, it's going to move in front of something else. So what's happening in this picture up here? The planet's moving in front of the star, exactly. How am I going to use that information to tell if there's a planet there or not? Light's going to curve around, not just curve around the planet, but actually make the star a little bit dimmer because the planet's in front of it and blocking the light coming from it, right? If a moth flies in front of the projector light, then what's going to happen to the light on the screen? Part of it's going to be blocked out, exactly. So if the star normally looks this bright, okay, here's time in this graph, here's brightness in this graph, and I'm watching the star, and the star's always the same brightness because why wouldn't it be? It's a star, you know, the sun's always the same brightness. But then all of a sudden, the star gets a little dimmer, and it's dimmer for a while, and then it goes back up to being as bright as it always was. Then the reason it got a little dimmer is because something passed in front of it. And the most likely explanation is that it has a planet that passed in between you and the star, and so it made the star a little bit dimmer while it was in front of it. Then it goes away, and the star is back to being bright, and it comes around again and it gets dim. Then it gets bright again. Then it comes around and it gets a little dimmer, and it gets bright again. So the transit method is watching the star night after night after night after night and measuring when it gets a little tiny bit dimmer, and then you can tell that it's because the planet just passed in front of the star. It takes very precise measurements to notice the difference. It's a very small drop. The analogy is, imagine you're looking at the side of a Las Vegas hotel, all right, skyscraper hotel, and all the lights are on in all the rooms, okay? And then one person lowers their blinds by 2 inches. That's the amount of difference between light and darkness that's between here and here. So it's a very, very, very faint measurement. So it takes very precise and powerful telescopes to watch this. But the benefit is, if it's going to happen, it's going to happen. And I just have to sit there and wait and watch. So it's as easy as watching and waiting and taking measurements. This is how Oops, ignore that for a second. That method is how we found almost all of the planets that were in that diagram at the beginning. In fact, they made a specific telescope that was just designed to do that one thing, that one job. Watch the stars over and over again and watch for the dip in the lights. And they sent it into space so that it wouldn't have the atmosphere to worry about. Has anyone heard of that? What the name of that is? I think I mentioned it once a while ago. Kepler. Good. Yeah, the Kepler Space Telescope. And all its whole job, it wasn't to measure a whole bunch of stuff. All it did was watch these stars right here, over and over, forever, never looking away, and so that it could always see these stars. If any one of them had a little dip in the brightness because a planet passed in front of it, then you could measure it. And just by watching that one little patch of sky for, I think it was 3 or 4 years before it ran out of juice, then it found thousands of planets by watching that. And the very last method is what you might have thought of as the most obvious one, is take a picture of the planet. Just a direct image. Take a direct picture of the planet. Why do you think it might be difficult to take a picture of a planet around another star?
Is it so far away?
It's so far away that the distance between them when I'm looking at them, they're the same blob, basically, you know, because there's the star. Even if that planet's thousands of miles away from the star, if they're both millions of miles away from me, then they're just one single speck. So it's hard to get this as a different image than this one. And the easiest way is to put a specific apparatus on your telescope that will block out the star so that you can't even see the star. So put a big black disc over it so that all that's left would be anything that's around it. But it's very difficult to do. And usually planets aren't discovered for the first way by taking a picture of them, but after they know it's there by one of the other methods, then they might try and go and take a direct image of them after the fact. This image in particular is only possible because you see the distance between this star and this planet is 55 astronomical units. That means it's 55 times further away from the sun as we are from our sun. So if we were 55 times further away from the sun than we are, that would be the same distance between this star and this planet. So they're really far away, so they can distinguish them between each other. Here's the new image. That first graph was from like 1.5 years ago. This is from much more recently. When the Kepler telescope we were just talking about, when it released its first batch of planets, the planets' numbers before were these blue bars. Here's what was known before Kepler telescope was working. And then Kepler released all the new things it found, and it shot up to these orange bars. The number of small planets, Earth-sized planets, went up 400% the first time Kepler released its first batch of science information. So Kepler found a whole lot of planets, and they're still digging through the information to find more of them. So that's just to tell you how we know the things we know, just in general. That convincing you that we do have ways of finding out that there are planets around other stars, and how big they are, and how massive they are, and a whole lot of other properties too. Here's what they found. Here's the whole point. What they found is that most other star systems don't seem to follow the same pattern that ours does. We have the 4 small, hard, rocky planets on the inside, and then the 4 big, gassy planets on the outside, and it's a very distinct pattern. Most other star systems don't have that pattern, or really any pattern whatsoever. It looks like we are pretty special in the grand scheme of things. That our particular arrangement is close to being unique. What you see on the board is some examples of what other star systems look like. Do you notice any particular pattern in any of those? From one to the other?
They're all round.
They are all round. Planets do go around the star, yes. No square orbits. You have not broken physics, no. But no, see, some of these star systems, and these are just a small example, obviously, but some of them only have one planet. Some of them have just a couple of planets. Some of them have really big, huge planets close to their star, unlike ours. Most of these star systems are not very big. You know, Jupiter, Saturn, Uranus, and Neptune are way out there for us. For some of these, they're all scrunched in to the middle. So there are a lot of strange things that we see in other solar systems, which gives us a lot to think about and a lot to learn. Because when we just had one example, our solar system, we had small rocky planets on the inside and big gassy planets on the outside. Why wouldn't it work that way for everyone else? Then we start finding all these other solar systems, and we find, you know, big, huge gassy planets close to the sun. And instead of having all these planets spread out, we find solar systems where all the planets are bunched up really, really close to the sun. Or we find examples of, you know, instead of having 8 planets like we do, a lot of star systems have 2 or 1 or 3 instead of a lot of them. So we found a lot of interesting things that we're going to have to come up with some new theories to explain why and how these things came into existence. Here's some of the main differences we found between our solar system and others. We found a lot of things called hot Jupiters. We call them that because they're big gas giants but instead of being really far away from the star, where do you think they are?
Really close.
Really close, which makes them really hot. So big gas giants close to the star. We found bunched up systems. All right. If I draw a little diagram of our solar system, all right, here's the sun, and all of here's Mercury, here's Venus, here's Earth, here's Mars, going around and around. Here's like a map of our solar system, okay? All the planets are spread out, and then Jupiter's even further away, and Saturn's even further away. You know, Pluto would be down here on the floor. They're so far away. We found a lot of star systems where here's the star, and it has 5 or 6 planets all real bunched up real close, like in the same distance that Mercury is in our solar system. So we found a lot of star systems where the planets are all very, very close to the star. Very different than ours. Our solar system that's big and spread out over all this area. Another oddity is small number of planets. A lot of the solar systems that we've been able to identify so far only have 1 or 2 planets that we can tell, not 6, 7, 8, 9 like ours is. there's, at least before this last big batch of Kepler information, I think that there was only like one star system that had more than 6 planets that we found. Out of all the thousands of planets, only one of the stars had more than 6 around it. And we have 8 major planets. So we have a lot compared to the other star systems we've been able to find. So I want you to be thinking about, especially when we start the activity, some ideas about why these things might happen. Because you know all about our solar system, our pattern, and you know the reason why we have small rocky planets here, and the reason why we have big gassy planets here, and it makes sense for our solar system. So how can you apply that information to explain these things that we see, to explain how I can get a Jupiter planet that's actually close to the star, or explain, why I can have these other arrangements that I'm looking at. Be thinking about that as we do the computer program. So you should all be booted up. Okay. Mrs. Rottinghouse installed a program on these several weeks ago for me. So now we just have to find where it is. As always, be checking your battery level. I think my charger fits at least the Dell one, or that model of Dell. If you're about to die. All right, can I borrow yours? I'm going to look at the website. Let me get her on the phone. Hi, this is Mr. Jones. Do you remember the NASA program that we got installed on our laptops? We're having trouble finding it on some of them, or actually any of them. Would there be a special place to look, or should it just be on the normal list of programs? Okay, I'll send one over. Thanks. Does anyone want to run theirs down so she can look at it? How about you do that? All right, as we're waiting on that, let's just start the next thing. So we're going to work on this side of the sheet. Turn it over to this side of the sheet. All right, this side of the sheet has a number of questions. It's a worksheet that you're going to be working on. Instructions for the first 3 questions are to use there they are. Use an extra sheet of paper to write your answers on, so there's definitely not enough room on this to have a blank sheet of paper. Your answers are going to be long answer. It should be 3 or 4 sentences. Unless you are part of the modified group, then you only have to answer 2 or 3 sentences. Answer the questions 1, 2, and 3. And question 4 is a really long answer. It's the critical thinking question. It's going to talk about what we were just addressing up here. So let's go through the questions quickly together. Number 1, describe the radial velocity method used to detect planets orbiting other stars. It's one of the things that was just on the presentation. Number 2, what does it mean for a planet to transit a star, and what can we learn from that? Hi.
NASA Exoplanet Explorer. So it's from the NASA JPL, Jet Propulsion Laboratory website. No. Okay, thanks. She's looking.
All right. Question number 3. What is a hot Jupiter? And then question number 4 is a big one. Question number 4 says many solar systems feature characteristics that are very different from our own, like we just talked about. And it gives you some examples. And the point of question 4 is for you to brainstorm reasons why these differences could have occurred based on what you know about our own solar system. So you know the reason our terrestrial and gas planets formed. Use those ideas to try and explain somehow these things, these other differences that you see in other solar systems. Any questions about the instructions? All right. The worksheet is a partner worksheet, so you can work with your seat partners that you have assigned, and you two up here in the front can get together for the worksheets when he returns, if that's possible, if he ever does return. If he doesn't return, I'm going to do my best to get the program up on my computer, because I shouldn't have any restrictions about downloading things. Yeah. Just so you have someone to bounce ideas off of. Yeah.
I'll write down
Okay. Thanks. Exoplanet.
Did she have any ideas? No.
She's still working on it. Mr. Pick told me to come on that.
Yeah. Oh yeah, thank you.
Get some sunscreen.
Finalizing.
While that's finalizing, anyone have any questions so far? That's interesting.
Line cover corners.
Mhm.
Structure room two.
Mine is new. She stole mine.
Wait, it's not showing up on the.
It's not showing on my list.
This is a new one.
I was trying to download it on my own computer, but it's been finalizing for like 10 minutes. Log on.
This is all the ones picked in.
Go over and search for NASA.
If I say yes, then no. I was trying to look for this, but Z, let's see. Oh, I was gonna say what is not cute. So, go next. Alright.
You can search NASA.
That's why I wondered, it's probably gonna be her.
Yeah.
I don't know why mine's taking forever.
Well, you can watch it for a minute. I'm gonna try to get this for to log on and do more browser, and I'll just keep that all search.
This is the next day.
My notebook's gone. I lost it. It was somewhere in my locker. I'm sorry, I was gone to sleep an hour till the walk. They should be banned to go to school from the next time.
Alright, the good news is that at least it was on her login on these computers. So I'm just going to plug this in. The bad news is that it looks like it's either not on any computers like she said it was, or it's somehow tied to individual login administrator. Which, crap, I shouldn't have done that. Just a second. I just unplugged the cameras.